Hey, BC Calc, this is going to be your day 50 lesson. Day 50, we're halfway to 100, so that's exciting. We are going to be looking at today indefinite integrals by substitution. This is actually a technique that some of you have in class talked to me about, because I know maybe you use it a little bit in physics already, but we're going to explore this hopefully a lot more in depth in this course and sharpen up those skills for integrals by substitution. So for a warm-up, there's two questions on the front page here that I'd like you to try with partners next time in class, or maybe in small groups. Now, there may not be as much time as you'd like to work on these next time I see you. So what I'll say is start planning out what you might try to do to answer these two questions. So at least if you thought of them in advance, you can, when you work in a small group or with a partner, you'll have a plan of attack ready to go to answer these two questions. So one is about some properties relating to integrals there. And then we have, kind of looking back, a fourth order differential equation with these initial conditions. So just in case we're not familiar with the notation, it's probably been used here and there because it's not very typical that we go all the way up to a fourth derivative, but this would be the fourth order differential. So like d to the fourth y over dx to the fourth is defined as being cosine x. So with those initial conditions, start thinking about how we're going to work our way towards developing our equation for y. Okay. So we're ready to then move on right away to the next page. And on the next page here, we have some steps that we're going to take to be able to evaluate an integral that looks something like this. So within our integral, we're going to see a series of expressions, one that might be of the form f of g of x, so maybe some sort of composition of functions has taken place. And then we're hopefully going to be seeing somewhere else within the function the derivative in that expression with respect to the inside here. So if we can identify those pieces, we can then use a substitution process by following these steps. So step one is substitute u for g of x. So we're going to let this whole function g of x equal u. And what happens is when you take du dx, the derivative of u with respect to x, that's going to somehow match up with g prime of x dx. So that's going to become your du then. And we're going to get something in the form of f of u du. Okay. So we're going to integrate with respect to u, and then once we've integrated with respect to u, replace u with the function g of x, and write your final answer, simplify if needed, so that we get our integral back in terms of x's. So the trick is to look for a function and its derivative in order to choose the best u possible. So when I'm looking at this first example, we're looking at some sort of composition of functions that's taken place, and maybe the derivative of that inside piece hanging out somewhere in the expression here. So I hope what you're seeing here is that this is the composition of 3x minus 1 got plugged into the x to the fourth function. So if you think of this as being kind of your g of x function, notice how the derivative of g of x, g prime, is that 3 dx over here. So the best thing to do to be able to evaluate this integral is to let u equal the quantity 3x minus 1. So therefore, when I take the derivative of u with respect to x, that's just going to be 3. And more commonly, what you'll see is that we'll move the dx to the other side just so we can define that du is equal to 3 dx. So based on what I've now written down as my u substitution here, I can replace this integral with the following. Well, if 3x minus 1 is u, that's now u to the fourth. And 3 dx is equivalent to our du. So now we're going to integrate u to the fourth du, first with respect to u, and then of course we'll go back and back substitute our quantity u equals 3x minus 1. So there's a pretty easy integral to find. It's u to the fifth over 5. Don't forget about plus c there, right? These are indefinite integrals, so we need plus c. And then finally, since u is equal to 3x minus 1, the indefinite integral that we started with would be equal to the quantity 3x minus 1 to the fifth over 5 plus c. And once you get the hang of this, this will start to become a pretty fast process where you can find your u pretty quickly and then identify du, and from there be able to simplify. So if we take a look at number 2, taking a look at the product of these two functions, although in this instance we probably could multiply these out and then find the derivative of that expression, it might be a little bit faster to recognize that if we consider this to be u, x squared plus x, our du dx expression would be 2x plus 1. Therefore, du would be 2x plus 1 dx. So I don't quite see 2x plus 1 dx, but it's not that much of a jump to realize that 2x plus 1 times 3 is the quantity 6x plus 3. So if you want to sort of make these things look alike, you can take out a 3 as a GCF there and write 2x plus 1. And I'll leave this as x squared plus x dx for now. And remember that one of our properties of integrals states if you're multiplying by a scalar, you can bring that scalar to the outside. And then we get 2x plus 1 times x squared plus x dx. And there might be other kind of ways I rewrite this in the future rather than pulling out that scalar. But for now, I think this makes sense that I have my u right here of x squared plus x, and my du is 2x plus 1 dx. So we're going to now integrate 3 times the integral of u du. All right, and now that I have that, the integral of u is u squared over 2. So it's going to become 3u squared over 2, and I multiply by 3 plus c. And then, of course, replacing u with the quantity x squared plus x, we get 3 times x squared plus x squared over 2 plus c. Okay, so now that we're starting to get the hang of things here, let's do maybe one more together, and then I think you'll be ready to try one on your own. Taking a look at the next example, we have 6x squared times the square root of x cubed minus 2. If we're thinking about finding a u substitution such that du, the derivative, exists there, we're definitely going to be choosing u to be, if we have an x squared and x cubed, the higher power of the two. So I'm going to let u equal the entire quantity under the radical. Let u equal x cubed minus 2. And you don't want to include the radical there, because if you include the radical, the du is not going to match what we have with 6x squared as nicely as we would hope it to in that case. So let u just equal the quantity underneath such that du is equal to, this would be 3x squared. And I'm just going to keep the dx on this side, okay? So du is equal to 3x squared dx, and that's not quite what we have in here. We have 6x squared dx, but we can make a quick fix by saying, oh, if I do 2 times du, that would be multiply this side by 2, 6x squared dx. Perfect. Well, instead of putting 2 times du on the inside to account for this, I'm going to leave this as radical u du. And instead of putting the 2 on the inside, I'm just going to pull the scalar out to the outside. So that will be kind of a common step that you'll see taken, where when you have to adjust your du a little bit to make it match what's on the inside currently with our dx, multiplying by that scalar, just kind of pull it out to the outside. And now we have still our anti-power rule. If this is u to the 1/2, up it, so now it's 3/2. Divide out front, so right, that's 2 times, it's going to be 2/3 u to the 3/2 plus c. So this is going to become 4/3 as a coefficient. And since u is x cubed minus 2, you would write this as 4/3 of x cubed minus 2 to the 3/2 plus c. Or if you really like maybe converting this back to radical form, you can write it as 4/3 times the square root of the quantity x cubed minus 2 cubed plus c. So either way around it, I'm not too picky about it. I would assume you'd probably want to leave it this way just for simplicity purposes on your end. But keep in mind, if it were multiple choice, you'd want to be really familiar with both forms, just converting from that rational exponent back over to a radical. So you can see that I've encouraged you to try this one. I think you're at a point where now that you've seen the last 3 examples, see if you can identify a good value of u to choose, where you're going to sub it in, find du, and see if you can maybe manipulate it a little bit like we did in the last case to match what you have with your derivative dx. Okay. So if you get stuck on it, no big deal, but next time I see you, I will just show you the answer to number 4. All right, number 5, how about definite integrals? Well, the thing is that it works really the same exact way. I'm going to use my u substitution, define du, but once I find the integral, then I'll be able to plug in my bounds and be able to come up with our constant value as our solution in the end. So when I look at the quantity in the parentheses there, I'm hoping that stands out to you to be a good u substitution there. Let u equal 1 plus x to the 4th. And therefore, your du is going to be 4x cubed dx. Now, in this case, to get x cubed dx be equal to our du, you're going to have to multiply by 1/4 to make that happen, right? So 1/4 of du is going to equal x cubed dx. So in this one, the constant that I'll pull out on the outside is a scalar of 1/4. So it's 1/4 of the integral from 0 to 1. We might have to talk about that in a second. Of, let's see, it's going to be u cubed du. So if I use my anti-parallel, that's u to the 4th over 4. So u to the 4th over 4 times a 4th is really u to the 4th over 16. Okay. Now here's the deal. You can't use these bounds if you're going to leave things in terms of u here. So you have 2 options from here. Option 1 would be replace u with the x quantity up here. So let's do 1 plus x to the 4th over 16 and use the original bounds of 0 and 1. So that's one option. So let's just go ahead and see what happens if I do that. If I plug in 1 for x, I'm going to get on the top 1 plus 1, which is 2. 2 to the 4th is 16, and 16 divided by 16 is 1. Minus when I plug in 0 for x, that's going to become 1 up top, to the 4th is still 1. So it's 1 minus 1/16, which is 15/16. Okay, so that's all fine. But option 2 is you could leave it in terms of u, but you're going to have to adjust the bounds. So if I come back over here and I say, okay, well, the antiderivative was u to the 4th over 16, what are these 2 bounds right here? Well, to figure that out, let's go ahead and substitute in our bounds of 0 and 1 to our u substitution over here. So when x equals 0, the lower bound, what would u equal? Well, if x is 0, u is 1. And if x equals 1 for my upper bounds, well, if x equals 1, then u would be 2. So really quickly, you can establish your new bounds with u and say, okay, well, now I know what those are. It's from 1 to 2. And I should get the same exact answer that if we do 2 to the 4th, which is 16 over 16, minus that would be 1/16, we get a total of 15/16. So you might wind up being a u person eventually, where you kind of like leaving it with u and changing the bounds. Or maybe you're a person who likes subbing back in for x and then using the original bounds. It's really, I think, up to you. There might be cases later on where it's easier to choose one option as opposed to another. So we'll kind of mix it up here and there and see which method we like the best. Okay, let's do one more practice together with a definite integral here. So we have the definite integral from 0 to the cube root of 7 of x squared over the square root of x cubed plus 9 dx. Okay, so similar to what we saw in the other example with the radical, if you let u just equal the quantity underneath the radical, x cubed plus 9, then du becomes 3x squared dx, which is pretty close to what we have. We have x squared dx, so to make that happen, we need to multiply du by 1/3. So 1/3 du would be x squared dx. And now I can pull out 1/3 as my scalar here. The integral from, well, before I plug in the bounds, let's just integrate with respect to u at this point. So now we have 1 over the square root of u du. Okay, so we know that if we bring this up, that would be u to the negative 1/2. So add 1 to that power. So now it's 1/2. 1 over 1/2 out front would be 2. So it's 1/3 times 2u to the 1/2, which is the same thing as 2/3 radical u. Let's get some new bounds and just leave it in terms of u. Let's try that way and see if we like it. So the lower bound right now is when x equals 0. So when x equals 0, what's the lower bound for u? Well, 0 cubed plus 9 would be 9. And if x equals, I mean, this is a little weird, but if it's the cube root of 7, cubing the cube root of 7 makes it a 7 plus 9 for an upper bound of 16. So now we have our upper and lower bounds. And we like the 16 and 9, of course, because they're going to be nice when we take the square root. So you can leave the 2/3 almost even out front, right, while you plug in those bounds. So it's going to be the square root of 16, which is 4, minus square root of 9, which is 3. And 2/3 times 1 is 2/3. Sweet. So lots more u substitution to come, by the way. So if you do try some for practice and you're like, I'm not really sure, well, I'm going to encourage you to just try one more. I think you guys can do it. Try some different options with some trig here. If I wanted to integrate sine squared x cos x dx, see if you can come up with a good u substitution such that in the end, we can evaluate that indefinite integral. Back to indefinite there, okay? All right, that's it for day 50. So u substitution, pretty awesome process, allows us to be able to evaluate what look like complicated integrals in a much, much easier way. We'll go over those questions that were the try-its next time I see you. And don't forget to look back at that first page and see if you can start developing a plan for you to work on with some peers next time you're in class. Have a great day.